Hello and welcome back to our last video on vorticity. So we're looking at kinematics fields and we're talking about vorticity. And we're still pounding our way through relative vorticity. We just actually wrapped up with Cartesian coordinates and looked at vorticity and Cartesian coordinates. We're not going to use those so much. We're going to stick mostly with natural because it's a little bit easier to understand vorticity in natural coordinates. So we're going to define a new type of vorticity, and we're going to call it absolute vorticity. I'm not sure why they call it absolute vorticity. They probably should have called it total vorticity or something like that. But it's simply the sum of the Earth's vorticity and also the relative vorticity. Now this is standing out in space looking on the Earth. The Earth, you can see the swirls as a result of the wind, but then also the Earth is rotating, and that rotation imparts some spin as viewed from outer space. So we're going to call the sum of Earth and relative vorticity absolute vorticity, and we'll use the Greek letter eta. So mathematically, if we add the math that we've done already, we've figured out that the Earth's vorticity is 2 omega sine phi. Phi is the latitude, omega is the angular rotation of the Earth. Remember, 7.29 times 10 to the minus 5th radians per second. And then zeta is both curvature and shear. Remember, zeta is the relative vorticity, and that results from the wind flowing around curves and also shearing, curves and shear. We said that the curve vorticity is V over R, and the shear is V over N with minus sign out in front. So if we stick this all together, then we have absolute vorticity. Now, you've probably heard the term cyclonic and anticyclonic, and we're going to get a little bit more technical exactly what cyclonic is. If you study meteorology in the southern hemisphere, you probably study things exactly opposite the direction that we're studying here. So we want to make sure that we have a good understanding in case you guys want to move to New Zealand, South Africa, Australia, India, wherever. So cyclonic by definition means that the air is rotating in the same direction as the Earth's rotation. So you remember we had a demonstration in class where we rotated the Earth, and in the northern hemisphere, looking down on the North Pole, you see that the Earth is rotating counterclockwise, and if you're looking at the South Pole, rotating the Earth, going to the bottom of the Earth, looking at the South Pole, you'll see that it's rotating in the opposite direction. It appears as if it's rotating in the opposite direction, and that would be clockwise. So in the northern hemisphere, counterclockwise circulation is cyclonic. In the southern hemisphere, clockwise rotation is cyclonic. So we can define that as being either positive or negative. Remember, we said that cyclonic, what we said was, if you draw your S and N coordinates, then if N is pointing towards the center, remember S is along the streamline or the direction of the flow, if N is pointing to the center, then you have positive radius of curvature and positive vorticity. So in this case, in the northern hemisphere, cyclonic flow, what's counterclockwise, is defined as positive vorticity. Zeta is positive. In the southern hemisphere, if the wind is blowing clockwise, then when you draw your S and N coordinates, S is in the direction of the streamline or the wind, N is 9 degrees and out. So that means that your negative vorticity is actually cyclonic in the southern hemisphere. I know that hurts your brain thinking about that. So you can do the same arguments for anticyclonic. Anticyclonic is opposite the direction that the Earth is rotating. And in the north and southern hemispheres, they're different directions. Northern hemisphere, anticyclonic would be clockwise. In the southern hemisphere, anticyclonic would be counterclockwise. So in the northern hemisphere, if you got wind flow that is going clockwise, drawing the SN coordinates, we know that that is negative vorticity. Zeta is negative or less than 0. And that is opposite the direction that the Earth rotates, looking down on the North Pole in the northern hemisphere. So that would be anticyclonic, opposite of the rotation of the Earth. And in the southern hemisphere, looking at rotation that is counterclockwise, drawing SNN coordinates, that is positive vorticity. But compare that to the rotation of the Earth, and it's opposite the rotation of the Earth as viewed from the southern hemisphere, so that would be anticyclonic. I know this hurts your head thinking about this. So I've drawn or came up with a little diagram, or little table that shows you what's cyclonic, what's anticyclonic in the northern and southern hemispheres. And then also at the bottom, Earth's vorticity by definition is positive in the northern hemisphere, which is cyclonic, and in the southern hemisphere it's negative, but of course it's always cyclonic because it's the direction the Earth is rotating in that hemisphere. And then you can take a look at the colors. The colors red indicate positive vorticity, whether it be curvature or shear, and the blue indicates negative vorticity. And then the columns tell you for that hemisphere whether it is cyclonic or anticyclonic. So applying this, gosh, we looked at a lot of vorticity. And we actually do use these terms when we're looking at the atmosphere. For example, if there's a jet stream, you can see here a jet stream that's moving across Oregon and Washington, down across Nevada. And the winds are moving along at 150 knots, it looks like, at, I guess that would be eastern Washington, eastern Oregon. Not sure where that is. But you got very strong winds. Winds weaken as you move north into Canada and also weaken as you move south into California and the Pacific. So on the north side of this jet stream, the wind is circulating. Because of the shear, there's strong shear, the wind is circulating. Put a paddle wheel in the flow. How does it circulate? And you'll see that it goes counterclockwise on the north side. So we say that that is the cyclonic side of the shear, the cyclonic side of the jet stream, where there's positive vorticity. On the south side of the jet stream, if you put a paddle wheel in the flow, you'll notice that it's rotating. That paddle wheel will rotate clockwise, which is negative vorticity or anticyclonic shear. So when we talk about the jet stream, we talk about the cyclonic shear side or the anticyclonic shear side. How do you figure which is which? Put a paddle wheel in and you'll see which way it rotates and then compare it to what hemisphere you're in. There is a limit to the amount of negative vorticity on the south side of the jet stream. If you take atmospheric dynamics, you'll talk about inertial instabilities, and there is a limit to that. Also, the other thing, we like to look at vorticity in the atmosphere on the vorticity charts. And the vorticity charts help us visualize where there is positive or negative vorticity. And remember, vorticity is a result of curvature and shear. The way they label the vorticity, they do it in terms of numbers going from, in this case, I highlighted 14 to 18. The X's mean there's a maximum or the most vorticity in that region, and it gets weaker as you move away. Those lines, those dotted lines, are isoplex of vorticity. Sometimes meteorologists call those vorticity lobes. But as you move away from the center, notice how it changes. Those numbers, multiply those by 10 to the minus fifth, and that gives you the number of radians per second that rotation is there. Now this is absolute vorticity. Remember, absolute vorticity is the sum of Earth's vorticity and relative vorticity. When you see N's, those indicate minimums of vorticity, and you can see weaker vorticity in this area. And this is how we pick out ridges and troughs, because ridges have minimum vorticity and troughs have maximum vorticity. And when I say troughs, I'm talking about short waves. They help, vorticity helps us visualize short waves. Other places on the internet, you can get vorticity panels that are in color, and that's very helpful also. The red and Yellow areas indicate maximum vorticity, and the blues and greens, minimum vorticity. So why do we look at vorticity? As I mentioned, it helps us figure out where there are troughs and ridges through maximum and minimum vorticity. Also, you'll learn later on, probably the end of November, beginning of December, that vorticity is related to vertical motions in the atmosphere and also the movement of weather systems. So that's all we have for vorticity. I hope you enjoyed it.